Hello my dear friends, welcome back to our YouTube channel Invisible Threads. Hope all of you are doing well in this difficult period of time. So in my last video I have already discussed on electric potential and also the potential energy of different charge configuration including the electric dipole. We have also found the expression for the potential energy in the presence of some external electric field also. So now in this video I will focus on some numericals to get a better understanding on the idea of electric potential energy. So let's begin. So numericals on electric potential and potential energy. So our first problem looks like that membrane walls of living cells have surprisingly large electric fields across them due to separation of the ions. So the electric field is generated due to the separation of the ions. What is the voltage across an 8 nanometer thick membrane if the electric field strength across it is 5.50 megavolt per meter? One may assume that there is an uniform electric field. So this is the problem stated, and you can see this is the membrane wall A and B, two wall of the membrane, and you can see there is a separation of the ions. The A wall has the positive ion and the B wall has the negative ion. So the electric field is acting from positive ion to the negative one, and the thickness of the membrane wall is 8 nanometer is equal to 8 into 10 to the minus 9 meter. We know that the electric field has the two units, one is Newton per coulomb or volt per meter. So here the volt per meter unit has been used. So electric field has the magnitude of 5.50 megavolt per meter. It means 5.50 times 10 to the power 6 volt per meter. And the separation is stated as D is equal to 8 into 10 to the minus 9 meter. 8 nanometer I have written here. It means 8 into 10 to the minus 9 meter. So as we all know that the electric field is equal to potential per unit change in the displacement. So this is the electric field is equal to VAB. So this is the potential unit A and B wall divided by the separation between them. So I need to find the potential. So yes, I need to find the potential, the voltage across the thick wall. So it means electric field times the separation. It means 5.50 times 10 to the 6 times 8 into 10 to the minus 9 volt. So it means 44 millivolt. So this is the potential across the two walls of the membrane. So our next problem will be looks like an electron, number 2. An electron is to be accelerated in an uniform electric field of strength 2 into 10 to the 6 volt per meter. So this is the magnitude of the electric field. What is the energy in kilo electron volt is given to the electron if it is accelerated through 0.4 meter of distance? And the second question is, over what distance would it have to be accelerated to increase its energy up to 50 of giga electron volt? So for the first question, as we all know that the change in energy, so work done means the change in energy, and the energy will be stored in the configuration, or in case here it is electron. So work done we can write it as force times displacement. Force we can write it as charge times electric field times the displacement. So what is the amount of charge in the electron? It is 1.602 into 10 to the minus 19 of coulomb times the magnitude of the electric field. It is written here, you can see 2 into 10 to the 6 volt per meter. So times 2 into 10 to the 6, and the displacement is 0.4. So the unit, you can see from their units also it gets, if I product all the units, so the charge has the unit of coulomb, the electric field has the unit of volt per meter times the displacement has the unit of meter. So it becomes 1.28 times 10 to the minus 13 of joule. Again, from the definition of electron volt we can see that 1 electron volt means if one electron is accelerated in potential difference of 1 volt. So how much the work is done? The charge of the electron is 1.602 times 10 to the minus 19 coulomb times 1 volt. It means 1.602 into 10 to the minus 19 of joule. So this is the amount of joule here. In this case 1.28 times 10 to the minus 13. So I need to convert the joule into the electron volt. So 1.28 times 10 to the minus 13 joule is equal to how much of electron volt? So I need to divide it by 1.602 times 10 to the minus 19. So it becomes 800 kilo electron volt. So this is our for the first problem, first question. And for the second one, over what distance would it have to be accelerated to increase its energy up to 50 giga electron volt? So I need to find the distance and the displacement here. So for that you can see that the change in energy in the same as before. The change in energy is equal to 50 giga electron volt. It is given here. It means 50 times 10 to the power 9 electron volt. It means 50 into 10 to the power 9 times 1.602 into 10 to the minus 19 of joule, because 1 electron volt is equal to 1.602 into 10 to the minus 19 joule. So 50 into 10 to the 9 electron volt means I need to product it. So this is the amount of work done. So 50 into 10 to the 9 times 1.602 into 10 to the minus 19 is equal to, so again this is the work done is equal to charge into electric field into displacement. Here charge and electric field is given. I need to find the displacement. So what is the charge of the electron? 1.602 times 10 to the minus 19, and the electric field is 2 into 10 to the 6. I need to find the displacement. So I have taken it as x. So x comes out to be 25 into 10 to the 3 meter. It means 25 kilometer. So this is the amount of the displacement. So our next problem will be like, so you can see number 3. The following figure represents the electric potential as a function of x. Plot the corresponding electric field as a function of the x. It means the distance. So you can see from the figure that this is the x-axis and this is the y-axis. So the x-axis is the distance, and in the y-axis the volts are plotted here. So you can see this is the 1 2 3 4 5 x in centimeter, the distance, and the volt in up to 25 volts it is mentioned here. So you can see potential depends on x, because this is only in the x direction it is plotted. So we can use the relation E vector is equal to minus dv dx I cap, because the E will also act along the x direction, because del v del y and del v del z is equal to 0. It means the electric field has no component along y and z direction. So from the graph you can see when the x varies from 0 to 1, the slope is constant. It means dv dx is equal to 25 volt per centimeter. You can see within 1 centimeter the voltage increases from 0 to 25. So what is the slope? dv dx is equal to 25 volt per centimeter. As we all know that the electric field is equal to minus of dv dx, so it comes out to be minus 25 volt per centimeter. Similarly you can see from x up to 1 to 4, you can see from 1 to 4 the voltage is constant. It is 25 volt. So V is equal to constant is equal to 25 volt. So electric field, the magnitude of the electric field is equal to minus of dv dx comes out to be 0, because the voltage is constant. Again from x is equal to 4 to 5, you can see from 4 to 5 under the separation of 1 centimeter, the voltage again drops from 25 volt to 0 volt. So the dv dx comes out to be dv dx is equal to minus 25 volt per centimeter. So again the magnitude of electric field is equal to minus of dv dx is equal to 25 volt per centimeter. So the plot of electric field for various point along x-axis, we can plot the electric field like, so you can see from the figure that this is the along the y direction, this is the electric field, has the unit of volt per centimeter, and along the x-axis it is the distance. So you can see when the distance is from 0 to 1, this is obviously the 0. So when the distance is x varies from 0 to 1, the electric field has the negative value and the magnitude is minus 25. So it is up to there. From when this is 1, when the x varies from 1 to 4, the electric field is constant and it is 0, because E is equal to minus dv dx is equal to 0. So it has a 0 value electric field. Again in between 4 to 5, the electric field has a value of 25 volt per centimeter. So here it is 25. So this is called step function. You can see this is called step function. Like it's like a steps of the stairs. So this is the variation of the electric field with the distance. So our next problem will be like, number 4. The 4 charges are arranged at the corners of the square PQRS of side A. From the figure you can see this is the square. You can see from the figure PQRS, it is square. In the opposite point P and the R, there is 2 plus Q charge, and the opposite point Q and S, there is 2 minus Q charges located. So and the side of the square is small a. So find the work required to assemble these charges in this given configuration. And the question number 2 is, suppose a charge q prime is brought to the center of the square. You can see the center is mentioned here as O. I brought one charge q prime at the center of the square by keeping the 4 charges fixed at the corner. So I keep all the other charges like 2q and 2 minus q fixed at the corners. How is the amount of the work is required? So you can see from the figure that PQ, QR, RS and SP all has the same length of A because it is a square. PQRS is a square, and the PR and the QS are the diagonal of the square. It comes out to be root 2A, and O is the center of the square. So when suppose in the beginning the work done to arrange the charges is independent of the way and the order they are arranged, it means it does not depend that in the beginning I bring plus Q charge or this minus Q or this one, and in which path I have taken these charges in this configuration. It does not depends on either the path or the order they are arranged. So it is the conservation nature of the electric force. So suppose in the beginning the plus Q charge is brought at the point P. You can see this is a point P. Here it is plus Q charge is located. So as there is no other presence of other charges, so the work done is 0. So WP is equal to 0. So after that, suppose I bring minus Q charge here from infinity at that point. So how much the work is done? It means the charge is minus Q, the magnitude of the charge is minus Q. So minus Q times the potential at the point Q at that point due to the charge at P, because initially there is plus Q charge. So it will produce its own potential at the point of capital Q. So if I bring minus Q charge, it will experience the force due to the potential of the plus Q charge. So how much the work is done? So WQ to bring this minus Q charge at the point of capital Q, WQ is equal to the charge value minus Q times the potential due to the charge plus Q at the point P. It means minus Q times Q by 4 pi epsilon naught A. It means minus Q square by 4 pi epsilon naught A. Similarly, work required to bring plus Q at point R. So what is that? The plus Q times the potential at the point R due to the charges of this one and this one. So plus Q and minus Q will produce the potential at the point R. So the potential is 1 by 4 pi epsilon naught times Q by root 2A minus Q by A. So the WR comes out to be Q square by 4 pi epsilon naught A minus 1 plus 1 by root 2. Then the work required to bring minus Q at the point of S, because you can see there is minus Q charge. So when I bring minus Q charge from infinity at the point of S, it will feel the electric force due to the potential of plus Q, minus Q and plus Q here. So it will produce affect the force, it will feel the force due to 3 other charges. So what is the required work done? It means minus Q charge times the potential due to other 3 charges, minus Q square divided by 4 pi epsilon naught A times 2 minus 1 by root 2. So the total work done is equal to, for the assemble of this charge configuration, W is equal to WP plus WQ plus WR plus WS. So it comes out to be Q square by 4 pi epsilon naught A times minus 1 plus 1 by root 2 minus 2 plus 1 by root 2, and the final expression is minus Q square by 4 pi epsilon naught A 4 minus root 2 units. So the work done is the negative 1. So this is the expression for the total work done to assemble this charge configuration and to put the charges in the vertices of some square. So you can see that our second question was like that suppose a charge q prime is brought to the center of the square by keeping the 4 charges fixed at their corners, how the amount of the work is done required. So you can see there is plus q charge and it is the minus plus q charge here. So at that point there is opposite charges at the vertices. So in that point, if I add up all the potentials, it comes out to be 0, because this distance and this distance all are the same. So at the center the potential, if I add up due to all the 4 charges, it will come out to be 0. So as 2 plus q and minus q charges are placed at the opposite vertices of the square, the net potential at the center of the square is 0. So no net work is required to bring any external charge q prime at the center O. As the potential is 0, so the work done is means charge times the potential, so the work done comes out to be 0. So our next problem is like a proton of mass m and charge plus e and an alpha particle mass 4m and charge 2e approach one another with same initial speed v from initially a large distance. How much will this particle get to one another before turning around? So you can see from the figure, this is the proton of mass m and having the charge of plus e, and this is the alpha particle of mass 4m and the charge is 2e. So this is, they are approaching one another from the infinite distance. So at some, suppose when the proton comes at the point A and the alpha particle comes at the point B, they just turn around, means they just go in opposite direction. So, and the closest, let A be the closest distance before turning around. I choose the distance AB to be r. So I need to find the distance r, how close these two particles will come before turning around. So you can see initially both the particles have their kinetic energy. So before turning around, this kinetic energy, the sum of the kinetic energy will be equal to the potential energy at the distance of r of these two charges. So I can write here, right, that in this case the kinetic energy of the moving particle will completely transformed into the electrical potential energy at the point of the closer approach, that I have already told you. So the total kinetic energy is equal to half mv square plus half into 4mv square, because both have the initial velocity of v and the proton has the mass of small m, whereas the alpha particle has the mass of 4m. So the total add up of the kinetic energy is this much, is equal to the electrostatic potential energy. It means k q1 q2 divided by r. So the proton has the charge of e, the alpha particle has the charge of 2e divided by r. So where we can get that 2k e squared by r is equal to 5 by 2 mv square. From there we can get the value of r is equal to 4k e square divided by 5 mv square. So this is the distance of the closest approach. We need to find the distance. So after that distance, when the distance is there, when the distance gets closer, less than this value, so then the two charged particles will get turn around. So our next problem will be like problem number 6. Derive an expression for the electrostatics energy needed to assemble a charged sphere from an infinite swarm of infinitesimal charges located infinitely far away. Let r be the sphere radius capital R, capital Q be the total charge of the sphere, capital V its volume, and rho be its volume charge density. So what it means? So I need to calculate the potential energy of a charged sphere. It means, so suppose, so what is the idea of the physics here? You can see. So initially, suppose I choose one small sphere where the radius of the sphere r tends to 0. It means, so I choose a very small sphere of the r having, in the limiting case of r tends to 0, and the charge content there will be q1 is equal to rho is the volume charge density times its volume. It means 4 by 3 pi r cube. So now I need to add up layer by layer to make a complete sphere of radius, solid sphere of radius capital R. It is mentioned here, you can see the R be the sphere radius. So this is the idea, that I choose initially a very small sphere with the radius tends to 0, and after that I need to add up layer by layer and up to a sphere of capital radius capital R. So the way, so you can see here, the way to make a big sphere is to add layers to an already existing smaller sphere. So you can see this is the smaller sphere initially at the limit of r tends to 0, where plus q1 charge is there, rho times 4 by 3 pi r cube, and if I add another layer of thickness dr, so, and the inner surface has the radius of r, so you can see the charge in the shell here, in the thin shell, what it will be, q2 is equal to means charge density rho times 4 pi r square dr. So this is the volume. So you can see if they add up, it will become like this, and I need to add this layer many more, so it becomes a radius of capital R, a big sphere. So initially you can see that we can start with an initial sphere where its radius tends to be 0 and the layers will add up to infinite small thickness of dr. This step is repeated number of times that I have already discussed. The electrostatic potential energy for the 2 point charges, as we all know, U is equal to K Q1 Q2 divided by R, where Q1 is the charge of a small sphere of radius R tends to 0, having charge density rho. So Q1 is equal to rho times 4 by 3 pi r cube. The second charge is in a thin spherical shell of thickness dr that I have already shown in the figure. You can see this is the thin spherical shell of thickness dr. So how much charge is there? Q2 is equal to charge density times its volume. It means 4 pi r square dr. So here you can see this is the Q2 is equal to rho into 4 pi r square dr. So what is the amount of potential energy acting in between two charge Q1 and Q2? The two charges are separated by the radius of the solid sphere, the small one, that is the r. So I need to integrate to calculate the whole potential energy to find a sphere, a big sphere of radius capital R. So U is equal to K. Q1 means rho 4 by 3 pi r cube, Q2 means rho 4 by 4 pi r square dr divided by r, and the integration will be the lower limit 0, upper limit capital R. So you can see if I integrate 16 pi square rho square K by 3, 0 to r to the power 4 dr, where the rho, the charge density, the volume charge density, it's better to say, it means capital Q divided by 4 by 3 pi r cube. So the expression after I put the value of rho Q by 4 by 3 pi r cube, it is here. The potential energy comes out to be 3K Q square by 5R. So this is the final potential energy of the solid sphere having the radius of capital R, you can see. Now if the charge sphere of radius capital R is divided into two equal volume sphere of radius small r. So what you can see, the initial volume was 4 by 3 pi capital R cube is equal to 2 times same volume. So 4 by 3 small r cube, I assume that the smaller sphere have the radius of small r. So what is the relation between the new radius and the old radius? Small r is equal to capital R divided by 2 to the power 1 by 3. Now the potential energy for a single small sphere, what it will be, U prime, if I choose it as U prime, is equal to 3K. Now the charge will be half, so 3K Q by 2 its whole square times the divided by 5R, the small r. So I will substitute the small r value times, it means r divided by 2 to the power 1 by 3. So it comes out to be 3K Q square by 20R times 2 to the power 1 by 3. So here I put, you can see r is equal to r divided by 2 to the power 1 by 3. So this is for the single small sphere. For the two sphere I need to product it by 2. So it comes out to be 3K Q square by 20R times 2 to the power 4 by 3. So what is the ratio of the new potential energy divided by the old one? U double prime divided by U, it comes out to be 0.63. So when the sphere is not divided, having the radius of capital R, and when it is divided into two equal volume sphere of radius small r, so you can see the splitting of a charged sphere into two reduces the potential energy up to 63%, or we can get a loss of the potential energy of 37%. So when in the nuclear fusion process, so friends, you will see that in the nuclear fission process, when a bigger nucleus gets divided into some equal or some unequal sizes of nucleus, so its potential energy gets decreased. So my friends, I am concluding my discussion here. If you have any kind of suggestion or facing any difficulties, don't hesitate to let me know in this video's comment section. Stay tuned and keep supporting Invisible Threads. Do like, share and subscribe our channel with your family and friends as much as possible. Thank you.